I'm going to calculate the Sagnac effect, assuming that the speed of light is c with respect to source. A representative Sagnac ring consists of mirrors and a source of photons. This is the source. This is the source of photons. There's a beam splitter which sends the photons in opposite directions and collects them again into a single direction, leading them to an interferometer, and with the photons out of phase by the time they get around in different directions with the ring rotating. Now, once the photon is emitted from this rotating ring, it moves in a straight line with respect to the inertial coordinate system. But I'm going, now if you observe that track from the ring itself, in other words from the rotating coordinate system, what you see is the ring or the track is stationary, but the track of the photons rotates. So for example, I'm going to take a representative photon track in the source coordinate system, i.e. that the ring is fixed. Now, this track rotates at an angular velocity omega. So the photon, when observed from the stationary ring, the photon starts here, and as it moves along the track rotates. So after traversing a distance from here to here, the end of the path has moved a distance from E to F, which is R times the rotation angle theta. Now AE is equal to BF, is the length of the track L. T is the time it takes to get from one end of the track to the other, which is L over C. And then EF is equal to R times the rotation angle, and the rotation angle is the angular velocity omega times T. So that EF is equal to R omega L over C, which I call delta. Now, for the same, we get the same result in the opposite direction, except the photon path now is shortened, because if the photon starts off on its track from here, as it moves along, the track is moving counterclockwise, so it finally winds up over here after the track has rotated through an angle theta. And again, EF is equal to R theta, which is R omega T, and substituting gives that EF is R omega L over the C. So you've lost that amount, and here you've gained that amount, depending on which direction of rotation the photon is going. Now, I'm going to consider a general case of a rotating circuit. I happen to show one with 4 sides, and then what I have is when the photon starts off here, and it starts off, the end of this track moves an amount delta, which we calculated here. So delta 1 is R1 omega L1 over C. Then it starts off on its next track towards 2, and it rotates along that track. Delta 2 is R2 omega L2 over C, up to delta 4 is R4 omega L4 over C. If I add them, then I get that delta is the sum. In one case I wind up long, in the other case I wind up short. So the difference, the final difference in this distance is going to be delta counterclockwise, put that delta omega, so that's twice this sum, which is 2 omega over C sigma Ri Li, where I is equal to 1 to n times the number of nodes on the track circuit. I've shown just some typical or some representative examples here. I have a ring with a triangle. I believe that configuration is used in gyroscopes. And then I have the Sagnac experiment itself, which is a ring with a series of mirrors in this configuration. Now, in both of these cases, because R is constant for the ring, delta is 2 omega RL over C, and the difference in time is going to be the distance divided by the speed of light, c. So it's going to be 2 omega RL over C squared. Now, at this point, I really wasn't aware of the result of the next calculation, so I was suddenly discovered something when I did this. I said, well, let me take an arbitrary ring, just a closed any closed circuit, rotating about a point, rotating around the a center, and I'm going to look at it from the viewpoint of the from a source coordinate system. That's where this is stationary, and the track, every little track, every element of track is rotating. All right, just as this rotated when I looked at it from the source coordinate system, this element of track is rotating, and therefore the total change in distance as it goes around is going to be 2 omega and times the sum of Ri dLi, a sum of RdL, which is the integral of RdL. Is something, wow, that's interesting. So that for going for both directions, this sum, going in both directions, this sum now, the sum sigma RL becomes integral R dL, and dA, now from here, dA is 1/2 R dL, so the integral of R dL is twice the area. So that we get finally, for this arbitrary case, taking R dL as the area, that delta is 4 omega A over C, and if we divide by C, we get that the time difference for both directions, 4 omega A over C squared, where delta is the path difference, T is the time difference. And this is the most general case for a rotating closed loop. Then after I did this, it occurred to me that this also applies to this. So the final answer for any closed loop, I just didn't see it when I was doing it. But it's a good thing that I went through this sequence, because if I hadn't looked at that and thought about it, I never would have realized that this result over here, which is RdL, summation RL sub I is integral RdL for a closed loop. And then what made me think was, I looked at this and I said, wait a minute, this general case here is a closed loop. It's a closed continuous loop with a finite number of continuities. So this also applies, this result also applies for this case here. So the most general result for an arbitrary rotating loop is that given by this. So this is the result on the assumption that the speed of light is constant with respect to source, and that also is consistent with the Michelson-Morley experiment. Thank you.